Hello, wonderful people. Here we are, chapter 34, electric current. We're going to go through sections 1 through 5. This should take us under 20 minutes, and then there will be just a few questions of homework at the end. We're going to end on Ohm's law. And Ohm's law is the key to all electricity. So last week we talked about voltage. Voltage produces a flow of charge, or current, within a conductor. The flow is restrained by the resistance it encounters. So let's talk about those concepts. Flow of charge. There's a picture of water down below. You've got a big tub, and you can see the water level is higher. So that means that down where the pipe is going from left to right, there's a higher pressure on the left than on the other side. So water is going to flow from left to right through the pipe. There's letter A. Water flows from higher pressure to lower pressure. The flow will cease when the difference in pressure ceases. Right? This is basic, obvious, everyday sense. Now, if we put a pump in there and we pump the water out of the smaller tub on the right and put it back in the bigger tub on the left, now we can get water to flow continuously. And the difference in pressure from the big tub to the little tub is maintained because of the pump. Does that make sense? Of course it does. And that is how electricity works in a nutshell. The voltage is the height of the water. So you have a higher pressure, means there's a higher voltage. And the voltage is what pushes the electrons. So it's not water molecules, it's electrons flowing through the pipe. And instead of a pipe with a hole in it for water to flow through, we use a metal which allows electrons to flow through the metal nice and easy. That's exactly what we're going to talk about for the rest of this. Okay. Electric current is the flow of electric charge. And what is electric charge? Electrons. So in solid conductors, electrons carry the charge through the circuit because they are free to move throughout the atomic network. These electrons are called conduction electrons. And the protons are bound inside the atomic nuclei, and the atoms are locked in fixed positions. So here it is in the picture. The solid gray sphere represents the metal atom. So just imagine that's a copper. And then copper has all these extra electrons that aren't a part of that metal atom. So these electrons can just flow through the conductor nice and easy. Unlike insulators, like glass. So if that's the molecule of glass, and these are the electrons that are in orbit around, I'm sorry, electrons don't orbit in a molecule. So glass is made of silicon. This is the silicon atom. So these electrons all are bound up, being shared with the silicon atom next to it. So none of these electrons are going to want to move. They like being in that shell. See how each one has a shell full of 8? Does that ring a bell from chemistry class? So these shells are all full, so none of these electrons want to move around. Copper over here has all these extra electrons just sitting around, free to go wherever they like. Oh, same picture, just bigger. Should have been using this. So how do we measure current? We've talked about what an ampere is before. Nobody says ampere. We all say amp. An amp is the flow of 1 coulomb of charge per second. And a coulomb is, well, there it is, 6.24 billion electrons. I prefer to say 6 sextillion, 240 quadrillion, quintillion. See, I can't even get it right. Let's just call it a coulomb. 1 coulomb of electrons per second. If you have 1 coulomb of electrons per second going past this point in the wire, that is 1 amp. Okay, here's the most important part. As the electrons flow, skip this part. Here's what you need to know. If you have water in a hose and you put a little water in one end of the hose, then a little water comes out the other end of the hose. It happens almost instantly. Electrons work the same way. When voltage pushes a few in one end of the wire, So you push a few electrons in one side of the wire, a few electrons come out the other end. Does that make sense? Good. The point is, it's not the same electron. When you put one electron in on the left-hand side of the wire and one electron comes out the right-hand side of the wire, that's not the same electron. Just like it's not the same water that goes into the hose on the left. Now, after a while, you can push that bit of water so that one bit of water does come out the other end, but it takes a while to push that through. Same for electrons. Now, electrons, charges, do not flow unless there is a voltage. Something that presides a voltage is known as a voltage source. Batteries and generators are capable of maintaining a continuous voltage. And what is a voltage? It's a push. Voltage is what pushes the electrons. Steady voltage sources. In a battery, a chemical reaction releases electrical energy, and in generators, they take the mechanical energy from the engine and turn it into electrical energy. The voltage produced is available at the terminals of the battery or generator. Nah, don't worry about that. Should have taken that slide out of there. The voltage provides the electric pressure, or push. I much prefer to call it a push, to move electrons between the terminals in a circuit. Did you know that we call this side of the battery a terminal and that side a terminal? Not everybody knows that, but that's what we call the ends of a battery, the terminal. One's positive, one's negative. The electric company uses electric generators to provide the volts, 120 volts that come to your house. Blah, blah, blah. All right, while we're learning this, and it's still all a little new, it's easy to get confused between current and voltage. Current is the charge flowing through a circuit, and voltage is being impressed across a circuit. Impressed across, I don't like that phrase. Voltage is pushing the electrons through the circuit. Okay. How much the amount of charge that flows in a circuit depends on the voltage provided by the voltage source. The current also depends on the resistance that the conductor offers to the flow of charge, the electric resistance. That's a heck of a sentence right there. The current depends on the resistance that the conductor offers to the flow of charge. So if we have voltage pushing electrons into a wire and the electrons come out the other end, what is resisting the flow of electrons through the wire? The electric resistance. Now, this is similar to the rate of water flow in a pipe, which depends on the pressure difference and on the resistance of the pipe. Do we have a picture? Coming up. But first, let me talk about resistance. Resistance is measured in ohms. It's named after a Mr. Ohm who lived in France a couple hundred years ago. And instead of using the letter O for ohms, because O is used for too much already, we use the Greek letter omega. Get it? Omega. That's why they chose it. The insulation, usually a form of plastic on a wire, usually has a resistance well over 10 million ohms. The copper wire itself usually has much less than 1 ohm of resistance. It takes hundreds and hundreds of feet of copper wire before it gets to 1 ohm of resistance. Gold is the best conductor in the world. You could have a wire of gold go from here to the moon and back, and that would have less resistance than the copper wire that goes from here in the class to the switching station a few miles away. Okay, now we're going to talk more about that electric resistance. So that bucket, as you see, has a hole in it, a big hole and a small hole. More water is going to pass through the big hole than the small hole, even though they both have the same pressure pushing water out. The same is true for voltage. If you have voltage pushing current electrons through something, if it has instead of the size of the hole, like for water, it's the resistance of the material. And here's the example. We have the pump pushing the water this way. It goes through a valve. And then here is where it goes back and forth, back and forth, back and forth. And it takes energy to do all that twisting and turning. And then it comes back and it gets pushed through again. It's the same idea in the battery circuit. The battery has the voltage that's pushing the electrons out, and it goes through the switch that's closed, and then through a resistance. And sometimes it's something like this, where the electrons are going back and forth, back and forth. It's really hard to get through the material. And then the electrons come back in and go back into the battery. So those same electrons can just keep getting pushed around and around and around. Oops. And here's where we define electric resistance. The resistance of a wire depends on the conductivity of the material in the wire and on the thickness and the length of the wire. So, thick wires have less resistance than thin wires, just like the pipe. A bigger pipe has less resistance to water flow. Longer wires have more resistance than short wires because there's more material. And electric resistance also depends on temperature. And most of the time, the higher the temperature, the higher the resistance. And here we are, the point of it all. Ohm's law. Current equals voltage divided by resistance. So, that's called Ohm's law. The relationship between voltage, current, and resistance. So how much current you get depends on how much voltage. More voltage means it's pushing harder. And if it's going through a certain resistance, then that's what resists the push from the voltage. And if there's a lot of resistance, you get less current. If there's a little resistance, you get more current. That's what we're going to practice for the next couple days in the homeworks. Examples. So here's the first problem. How much current is drawn by a lamp that has a resistance of 100 ohms when a voltage of 50 volts is pushed across it? Voltage is 50 divided by 100 ohms, and you get 1/2 of an amp. Ta-da! It really is that simple. And the only way I make it harder is instead I will give you current and resistance, or I'll give you voltage and current. That's all there is to it. Yeah, that's a nice little way to phrase it. So voltage supplies the push to the electrons, resistance in the material that the electrons are flowing through. The resistance opposes the push, and current results when electrons flow through the material. Do you like that? Is that a nice short summary of it for you? I hope so. Oh, and that is that. So good luck. The homework is short and sweet. And if you have any questions, please don't hesitate to ask. Thank you so much. Good luck. Bye-bye.